So let us consider we have this vector A bar and we have this vector B bar. Theta is the smaller angle between these two vectors. So if we complete this parallelogram, so this is O, P, Q, R. This diagonal gives the addition and this diagonal gives the subtraction of these two vectors that we have seen. Now here we want to show that the magnitude of this cross product of two vectors represents the area of this parallelogram. So for that purpose, if we draw the normal from the end point of B bar on A bar, if we draw the projection of B bar along A bar, then this side is H. This side is H. So this is nothing but the height of the parallelogram, and the magnitude of vector A bar is nothing but the base of the parallelogram. So we know that the area of a parallelogram is expressed as the product of base into height. The area of the parallelogram is expressed as the product of base of the parallelogram into the height of the parallelogram. So base here is nothing but the magnitude of vector A bar, and the height of the parallelogram is considered to be H. So this is nothing but AH is the area of this parallelogram. Now what is H? What is H? If we consider mod B bar, or simply B is the magnitude of vector B bar, then this H is nothing but B sin theta. Here H is nothing but equal to B sin theta. So using the value of H as B sin theta, we get the area of parallelogram is equal to A into H is to be replaced by B sin theta. So it is AB sin theta, and this AB sin theta we have seen is nothing but the magnitude of the cross product of the vectors E bar and B bar. So what we observe is that the area of this parallelogram formed by the two given vectors A bar and B bar as the two adjacent sides is nothing but equal to the area of this parallelogram is nothing but equal to the magnitude of the cross product of two given vectors. So that is how we can say that the magnitude of the cross product of two vectors gives us the area of the parallelogram formed by the two given vectors as the two adjacent sides. So that is all about the vector product or the cross product of two vectors. And next we are going to study the some examples of the cross product or the vector product are given. Let us see in which situations we come across the situation that the product of the two vectors results into a vector quantity. The examples of this vector product or cross product. The first example is the moment of force. The moment of force is a vector quantity and it is expressed as the cross product of the position vector of the point of application of the force and the force vector. So the moment of a force is expressed as m bar is equal to r bar cross f bar. So the result of multiplication of these two vectors results into a vector quantity. So this is the first example of the cross product of two vectors. Then the angular momentum. The second example is the angular momentum. The angular momentum L bar is expressed as the cross product of R bar and P bar, where R bar is the position vector and P bar is the linear momentum. R bar is the position vector and P bar is the linear momentum. So the product of these two vectors results into a vector quantity, that is angular momentum. And the third example is the force acting on a charge Q moving in magnetic field. The force acting on a charge Q moving through a uniform magnetic field of induction B bar. This force is given by F bar is equal to Q into bracket V bar cross B bar. Here Q is the quantity of charge that is moving with the velocity V through a uniform magnetic field of induction B bar. So this force is nothing but the electromagnetic force acting on moving charge through the magnetic field, and this expression was observed by the scientist Lorentz. So this equation or this force is called as Lorentz force and the equation is called as Lorentz equation. So this is the force, Lorentz force acting on a moving charge through a uniform magnetic field with the velocity v. So these are certain examples of the vector product of two vectors, and with that we'll close it here for this video, for this lecture. Next time then we shall start to study the new concept that we are going to introduce with this year. Whatever we have studied till now in previous 2-3 lectures or 2-3 videos, all that we have already studied. It was just the rapid revision that you have studied earlier, and whatever the new that you want to study, that we are going to study in the next coming videos. Okay, thank you. Good morning. In the last video, we have studied the scalar product or the dot product of two vectors. So today we shall discuss what is the vector product or the cross product of two vectors. We have said that if the result of multiplication of the two vectors yields to be a scalar quantity, it is called as scalar product or dot product of two vectors. But if the result of multiplication of the two vectors yields to be a vector quantity, such product of two vectors is called as the vector product, or it is also called as the cross product of two vectors. And this cross product, if we have the two vectors A bar and B bar, and if we take the vector product or the cross product of these two vectors, and since it results to be a vector quantity, let us consider the vector C bar represents the vector product or the cross product of two vectors. Then this resultant is expressed as, say, C bar is equal to A bar cross B bar. So this is how we represent the vector product or the cross product of two vectors. And this is again expressed as n cap into a b sine theta, where a and b are the magnitudes of the two given vectors a bar and b bar, and theta is the smaller angle between the two given vectors, so that we can write 0 is less than or equal to theta is less than or equal to 180 degree. And this n cap represents a unit vector in the direction of the vector a bar cross b bar, or in the direction of c bar. Now, this cross product or the vector product of two vectors as well can be expressed as, suppose pictorially we can represent it like this. Suppose we have this vector a bar and we have this vector b bar, and theta is the smaller angle between these two vectors. Then the vector c bar representing the cross product of a bar and b bar is found to be directed perpendicular to the plane of a bar and b bar. If we imagine that the vectors a bar and b bar lie in the horizontal plane, then the vector c bar representing the cross product of a bar and b bar will lie in the vertical plane, because a bar and b bar are lying in the horizontal plane. So this c bar or a bar cross b bar is always perpendicular to the plane of a bar and b bar, right? Okay. Now, if this vector c bar is perpendicular to the plane of a bar and b bar, then whether this vector c bar is directed in the upward direction or in the downward direction, how to know it? So the direction, the magnitude of this vector a bar cross b bar, magnitude of a bar cross b bar is expressed as a b sine theta. This gives the magnitude of this vector a bar cross b bar. How to know the direction of this vector? The direction of this vector c bar is obtained by using the right hand rule or right hand screw rule. What is this right hand rule? You know well. If we curl the four fingers of the right hand in the sense from the first vector in the product towards the second vector, then the stretched thumb denote the direction of the vector a bar cross b bar. So in this case, since vector a bar is lying towards right and b bar is lying towards left, and if we curl the four fingers of the right hand in the sense from the first vector in the product towards the second vector, since the thumb is stretched in the upward direction, the vector c bar will be perpendicular to the plane of a bar and b bar and will be directed in the upward direction. This is the direction of a bar cross b bar. This vector c bar is nothing but equal to a bar cross b bar, and it will be perpendicular to the plane of a bar and b bar. So this is the right hand rule. What is right hand screw rule? Let us consider we have a right handed screw. Suppose we have this right handed screw and we have the vector a bar here. This is the vector a bar and this is the vector b bar. Theta is the smaller angle between these two vectors. Now, if we rotate this right-handed screw in the sense from the first vector in the product towards the second vector, and if we observe in which direction does the tip of this screw advances, this direction in which the tip of the screw advances gives us the direction of the vector C bar representing the cross product of A bar and B bar. So here, if this right-handed screw is rotated in this anti-clockwise direction, that is from the first vector in the product towards second vector, then the tip of this screw advances in the upward direction, so that the direction of the vector C bar will be directed in the upward direction. However, if we try to evaluate the cross product B bar cross A bar, will it be same as like this? No. Because, let us see. If we evaluate the cross product B bar cross A bar, what you will observe? You will observe that this cross product then can be expressed in magnitude and direction as n cap BA sine theta. So n cap here is the direction of the vector B bar cross A bar, and magnitude of B bar cross A bar is BA sine theta, which is same as AB sine theta. So that the magnitude of A bar cross B bar is same as the magnitude of B bar cross A bar, but the direction of this B bar cross A bar will be different than the direction of A bar cross B bar. Why? Let us see. So if we apply the right hand rule in order to obtain the direction of the vector C bar, or say C1 bar, representing the cross product B bar cross A bar, what we have to do is, we have to curl the four fingers of the right hand in the sense from the vector B bar towards the vector A bar, so that the vector C bar in this case is found to be directed in the downward direction. So this is the vector C1 bar representing the cross product B bar cross A bar. So this vector C1 bar, that is B bar cross A bar, is found to be different than the vector A bar cross B bar. So this vector A bar cross B bar is found to be directed in the upward direction, so that the vector C1 bar representing the cross product B bar cross A bar will be directed in the downward direction. Again, it will be perpendicular to the plane of A bar and B bar, but is found to be directed in the downward direction. Similarly, by using this right hand screw rule also, we can know the direction of this vector C bar representing B bar cross A bar. So in this case, we have to rotate this right handed screw in the sense from the first vector in the product towards the second vector, that is from B bar to A bar, that is in the clockwise direction. So if we rotate this screw in the clockwise direction, the tip of the screw is found to be directed in the downward direction, so that the vector C1 bar representing the cross product of B bar and A bar will be pointing in the downward direction and perpendicular to the plane of A bar and B bar. So that is how we can know the direction and the magnitude of the cross product of two vectors. Now we'll see some properties obeyed by this the characteristics of this cross product. The first and the most important characteristic of the vector product is that characteristics of cross product or vector product of two vectors. The first characteristic is that if the two vectors are parallel or anti-parallel to each other, such that theta between the two vectors will be either 0 or 180 degree respectively. So if the two vectors are parallel to each other or anti-parallel to each other, if the two vectors are parallel, the angle theta between them will be 0, and if the two vectors are anti-parallel, then the angle theta between them will be 180 degree. So if it is so, what will be the value of sine theta? The value of sine theta in both the cases will be equal to 0, because sine 0 is 0, sine 180 degree is again 0. So if it is so, then what will be the cross product of a bar and b bar then? If we have these two vectors a bar and b bar, such that the two vectors are either parallel to each other or anti-parallel to each other, this cross product will work out to be equal to 0, because since it is expressed as n cap a b sine theta, though the magnitudes of a bar and b bar are non-zero, since the value of sine theta works out to be equal to 0, the cross product of two vectors works out to be equal to 0 if the two vectors are either parallel to each other or they are anti-parallel to each other. So this is the first characteristic of the cross product or vector product of two vectors. If it is so, then if the two given vectors are equal, what can we say? If a bar is equal to b bar, then we can express it as a bar cross a bar. And if we evaluate this cross product will be again equal to 0. That is, the self cross product of a vector is equal to 0. The self cross product of a vector is equal to 0. And from this, it follows that if we consider the two vectors are nothing but the unit vectors that we use in case of the rectangular coordinate system along the positive directions of x, y and z axis respectively, then we can write the cross product of the unit vectors along x axis, that is I cross I, the cross product of the unit vectors along y axis, that is j cross j, and the cross product of the unit vectors along z axis is again equal to 0. That is, I cross I, j cross j and k cross k works out to be equal to 0, because these unit vectors are parallel to each other, or we can say it is nothing but the self cross product of the unit vectors. And here we observe that the self cross product of the two vectors is equal to 0. So because the angle theta between them is 0. So this is the first characteristic of the cross product. Now the second characteristic is if the two vectors are perpendicular to each other. The second characteristic is if two vectors are perpendicular to each other. If the two vectors are perpendicular, then the angle theta between them will be 90 degree. And if theta is 90 degree, this implies sine theta to be equal to 1. So that the cross product a bar cross b bar will be equal to n cap into ab, where a and b are the magnitudes of the two given vectors and n cap is the unit vector in the plane perpendicular to the plane containing a bar and b bar. So sine theta is equal to 1 here. So that is how we can express the cross product of two vectors which are mutually perpendicular to each other. Now if we evaluate the cross product of the unit vectors, what will be the cross product of unit vectors? Let us see. So if we evaluate the cross product of I with Z, since I cap is directed in the positive direction of x axis, j cap is pointed in the direction of positive direction of y axis, these two unit vectors are mutually perpendicular to each other and such that the angle theta between them is 0. So sin theta will be equal to 1. And since I and Z are the unit vectors, their magnitudes are 1 each. So this is equal to n cap only. And in this case, what will be n cap? N cap is nothing but the unit vector in the direction perpendicular to the plane of I cap and j cap, that is perpendicular to the xy plane, and the direction perpendicular to xy plane is nothing but the z direction. So that I cross j will be equal to k cap. So I cap cross j cap works out to be equal to k cap. Similarly, we can write j cap cross k cap is equal to I cap, and k cap cross I cap is equal to j cap. So that is how, if we maintain the cyclic order of these unit vectors, then the resultant representing the cross product will be directed in the positive directions of z axis, x axis and y axis respectively. However, if the cyclic order of these unit vectors is reversed, what will happen? So let us see, j cap cross I cap, this resultant vector will be perpendicular to the plane of I cap and j cap, but will be directed in the downward direction, that is in the negative direction of z axis. So it will be minus k cap. The cross product k cap cross j cap will be equal to minus I cap, and the cross product I cap cross k cap will be equal to minus j cap. So if the cyclic order of these unit vectors is reversed, the direction of the resultant vector representing the cross product of these unit vectors also gets reversed, right? Okay, so this is the second characteristic of the cross product. Now we can evaluate the cross product of the two vectors in terms of their magnitudes of the components of the two given vectors. In terms of the rectangular components, we can evaluate the cross product of two vectors in terms of their components. In terms of the rectangular components, the two given vectors can be expressed as a bar equal to I cap ax plus j cap ay plus k cap az, and the vector b bar will be expressed as I cap bx plus j cap by plus k cap bz. This is how we can express the vectors a bar and b bar in terms of their rectangular components. So now if we want to evaluate the cross product of these two vectors a bar cross b bar in terms of these rectangular components, we can express it as I cap ax plus j cap ay plus k cap az cross into second bracket I cap bx plus j cap by plus k cap bz. And if we take the product of these two brackets, this product can be expressed as first term will be I cap cross I cap ax bx plus I cap cross j cap ax by plus I cap cross k cap ax bz. Then plus j cap cross I cap ay bx plus j cap cross j cap ay by plus j cap cross k cap ay bz plus k cap cross I cap az bx plus k cap cross j cap az by plus k cap cross k cap az bz. So this is how we can express the cross product of the two vectors. Here, these three terms, I cap cross I cap, j cap cross j cap, and k cap cross k cap will be equal to 0 because it is the self cross product of the unit vector. So these terms will vanish or will become 0. So we can express this cross product as I cross j we know is k, so it is k cap ax by. Then I cross k is minus j ax bz. J cross I is minus k ay bx. J cross k is plus I ay bz. K cross I is plus j az bx, and k cross j is minus I az by. So this is how we express the cross product of two vectors. Now we can club the terms of I cap, j cap and k cap together. So if we club the terms of I cap, j cap and k cap, what will we get? Let us see. So this is equal to I cap into bracket ay bz minus az by plus j cap into bracket az bx minus ax bz plus k cap into bracket ax by minus ay bx. So that is how we express the cross product of these two vectors E bar and B bar in terms of their rectangular components. So this again can be expressed as I cap ay bz minus az by minus j cap into bracket ax bz minus az bx plus k cap into bracket ax by minus ay dx. And this is nothing but the determinant of unit vectors I, j, k, the components of the first vector in the product, and the third row is the components of the second vector in the product. So we can express this cross product in the form of determinant. The first row of the determinant is the unit vectors I, j, k, The second the second row is the components of the first vector in the product, and the third row is the components of the second vector in the product. So this is how we can express the cross product of two vectors in terms of their rectangular components. Now let us see the laws that are followed in case of the vector product or the cross product. Laws obeyed by the vector product. The first law that is obeyed by the cross product or the vector product of two vectors is that the cross product A bar cross B bar is found to be equal to minus of B bar cross A bar. The first law obeyed by the vector product or cross product of two vectors is that A bar cross B bar is equal to minus of B bar cross A bar, because we have seen that the magnitudes of A bar cross B bar and B bar cross A bar are same, but the directions of these two vectors are oppositely directed to each other, and that is why we can express it as A bar cross B bar is equal to minus of B bar cross A bar. So this is the first property, the first law obeyed by this cross product. And from in case of the dot product, we have seen that A bar dot B bar is equal to B bar dot A bar. So we say that the dot product of two vectors obeys the commutative law of multiplication. But in case of the vector product or the cross product of two vectors, we observe that A bar cross B bar is equal to minus of B bar cross A bar. So what we can say is that the commutative law of multiplication is not obeyed in case of the cross product or the vector product of two vectors. The commutative law of multiplication is not obeyed. We cannot change the order of the vectors in the product. If the order of the vectors in the product is reversed, the sign of the direction of this resultant vector also gets reversed, or we can say that the sign of this product also gets reversed. So this is the first law that is obeyed in case of the cross product or vector product of two vectors. Then the second law obeyed is that if we want to evaluate A bar cross B bar cross C bar, then this cross product can be expressed as A bar cross B bar plus A bar cross C bar. So what we can say here is that the vector product of the vectors obeys, so here it should be A plus B, B plus C, it should be B plus C. So this is expressed as A bar cross B bar plus A bar cross C bar. So we say that the vector product of the two vectors obeys the distributive law of multiplication. It obeys the distributive law of multiplication. So this is the second law obeyed in case of the vector product or the cross product. Then the third law obeyed is if we want to multiply the cross product of two vectors by a scalar. Here m is a scalar, and we want to multiply this cross product of A bar and B bar with this scalar m. This product can be obtained either by multiplying the given scalar first to the first vector A bar and then take the cross product with B bar, or else first multiply by the given scalar to the vector B bar and then take the cross product with A bar, or this again can as well be expressed as we can first evaluate the cross product of A bar and B bar and then multiply this cross product by the scalar n. So we can evaluate this product in either of the ways. All these results to the same result. So this is the law that is obeyed by the vector product or the cross product of two vectors. And the last law that is obeyed by the vector product or the cross product of two vectors is the magnitude of the cross product of two vectors gives the area of the parallelogram with sides A bar and B bar. If we have the two vectors A bar and B bar, and if we evaluate the magnitude of the cross product of A bar and B bar, this magnitude of this cross product of two vectors is found to give us the area of the parallelogram formed by the two vectors as the two adjacent sides. How? Let us see. So let us see that how this magnitude of this cross product of two vectors gives us the area of a parallelogram formed by the two vectors as the two adjacent sides.